Okay, so I extend a warm welcome to all the participants here. So welcome to this webinar series hosted by IEEE Signal Processing Society's Delhi chapter as well as IIIT Delhi. Today we have with us an eminent speaker, Dr. Lovekesh, which from TCS Research. So introducing briefly our speaker, Dr. Lovekesh completed his PhD from Vanderbilt University, Nashville, USA. In 2015, he joined TCS Research, New Delhi, where he currently leads the deep learning research area. His team works on problems in reinforcement learning, robotics, NLP, vision, and sensor analytics. Welcome, Dr. Lovekesh. Over to you for the talk.
Thank you so much for inviting me for this talk. So we'll get started right away. So all of the attendees, especially students, you're living in a very kind of special sort of time from a technology perspective, because we're seeing very rapid advancements in not just AI, but a number of kind of fields that are very closely connected and will probably drive the future of technology within a very short span of time. Right? So the first of these, which are relevant for the discussion today, is the fact that sensor prices over the past decade or so have been rapidly declining. So it's much cheaper now to procure these IoT-enabled sensors for your application than it was, say, 15 years ago, because there are a larger number of vendors, there is economies of scale, and improvements in sensor technology as well. And then the second important development is in the rapid improvement in battery energy density, right? So now with companies like Tesla leading the way, you now have cars that can go up to 500 miles of range on a single charge. That was unthinkable 10 to 15 years ago, right? And the third big development, which is perhaps more well known, is the fact that networks are always getting faster. We are now, from 2G, 3G, 4G, and now we're about to have universal adoption of 5G enabled networks. So now, with all these three kind of areas developing as rapidly as they are, they're driving a world in which almost everything will be connected. You'll have connected cities, connected healthcare systems, connected factories, and manufacturing systems as well, right? And that's great, but that also brings up a problem in that now, with all these IoT sensors running all across the world, you are now generating petabytes of data or maybe more. And now what do you do with all this data, and how do you process it in a way that gives you the information that you really want? And this is where the role of data-driven AI, in particular techniques from deep learning, kind of emerge. So unless if you've been following the news, AI news at all, most of these headlines that you're seeing in this slide are probably going to be very familiar to you, right? It's just to kind of underscore the fact that deep learning has really been driving a lot of the AI developments over the past, let's say, decade or so. But applying deep learning to these enterprise IoT problems isn't a straightforward task, right? So, despite all the advances, you run into a lot of problems with noisy, messy, or sometimes missing data, because customers in the real world are not as hygienic with their data keeping practices as you might think. And then you have to worry about compliance with privacy and legal regulations. You have to worry about interpretability, especially for critical applications. You don't, just having a model that gives you 99% confidence isn't good enough. You need to know when that 1% error is happening and for what reason. The other big sticking point is that there's no principled way at the moment of incorporating explicit domain information into your deep models and in your deep learning. So deep learning is great for pattern recognition, not so great for, at least not so easy to incorporate prior knowledge into. Right? And then you have these scalable compute problems, right? So not every company has the compute capacity of a Google or a Facebook, and you need to optimize on the compute and memory footprints of these models in order to make them deployable on device at scale. Right. This is another model compression sort of techniques are being used here to solve this problem. And generally, customers have a much shorter ROI cycle than you might imagine. What that means is that they're not willing to spend, millions and millions of dollars before they see any returns. Generally, their patience in the enterprise world is much shorter, and you have to start delivering results much faster. And lastly, but most importantly, most of these enterprise applications will not be completely automated solutions. They will always be human in the AI loop, and there's always going to be human oversight to these systems, at least for the foreseeable future. And therefore, you have to enable techniques that kind of allow for this in a very seamless sort of way. So things like active learning and so on. Right? I mean, that brings, with all these challenges in mind, we started to kind of develop this iSense module for deep learning for time series data, in particular with a view towards IoT applications, right? And these are kind of the broad themes are within iSense. You have systems, you have algorithms and techniques for health monitoring and prognostics, which I'm going to discuss, and then some pre-trained models and meta learning enabled models for fast transfer and retention of knowledge across use cases. You have models for forecasting, and then the most exciting kind of current research is towards digital twins using neural networks. Right? So I'm going to dive right in and start describing the work within iSense. The first topic I'm going to cover is health monitoring and prognostics of industrial equipment, the kinds of which are kind of labeled in this slide. And the objective here is to given a sensor-equipped IoT system, can you estimate the health of this system in real time? Can you detect faults? And can you estimate when a system is likely to undergo catastrophic failure? Right? Now, when we started off on iSense, it was the year 2014. It was before TensorFlow or PyTorch or any of the libraries had really taken over the world. And deep learning was not as obvious a solution to these problems as it is today. Right? And in fact, most of the state-of-the-art models at the time, did something like point level anomaly detection or some kind of variant thereof. But there were significant challenges that remained unaddressed. The first of which was that these systems needed to model complex temporal dependencies across multivariate sensor data, high-dimensional multivariate sensor data. They had to account for missing and noisy readings, multiple operating conditions or modes, latent factors or control sensors, in addition to dependent sensors. And there were very few instances of failures, right? So in reality, in the real world, these large systems don't fail very often because there's always lots of checks and balances to ensure that they keep running. Right? So the question was, can deep learning based temporal models add value? As I mentioned, it wasn't that obvious at the time. But we started to embark on this journey, and and LSTMs were just about getting prominence in the translation world, and so we decided to see if they can be used for these sorts of tasks, right? And we found that they kind of met a lot of the criteria that we were looking for. They model dependencies between sensors or correlations between sensors. They model dependencies over time and dependencies at various time scales. And in addition to boot, they even composed hierarchical features with multiple layers, right? So with all this, we decided that this was indeed the way to go. And so the first problem we wanted to attack was the problem of detecting anomalies or faults in these IoT systems, right? And yeah, so imagine a system with hundreds or potentially thousands of sensors, and now you want to detect when something in that system has gone wrong or is about to go wrong, right? And so it's very difficult to model failures because, as I mentioned, there's very limited instances when these systems tend to fail in the real world. So you won't have a lot of failure data. And it's probably dangerous to model failures because failures can happen in 1,000 different ways. What you should be modeling, we decided, was we should be modeling the normal behavior when the system is healthy and the system is working as per norm. We should be modeling the data during that time and look at deviations from that behavior in order to model, in order to predict anomalies. And so that's kind of that was kind of the high level reasoning, and the thought was that once we are able to detect these anomalies via these deviations from normal behavior, we can then reason about which sensors actually cause these anomalies and diagnose the fault, not just predict the fault but actually diagnose what component or subcomponent of the larger system is causing the fault. And then finally, the objective was to forecast, how much time there is before this system actually collapsed and there would be a forced shutdown, potentially costing millions of dollars. Right? And this led us to our first algorithm, which is quite kind of well cited now. It's called LSTM-AD, which is basically what we did was we look at a lot of training data from normal behavior, and we train an LSTM model to predict that predict such a time series ahead. So given a certain window of time, can you predict what's going to happen in the immediate future, right? And what you do is you do this and you train this network over lots and lots of normal data. And now when you come at test time, when you're actually deploying this system, if the system fails to predict well, and there is a huge discrepancy between the estimated predictions and the actual targets, you use that to signal that something is off. The network is seeing something it has not seen before, and you flag that as a potential fault, right? And you use that as a proxy for what we call the health index of a machine, right? So health index is just kind of the inversion of of an anomaly score, which means that when the health index is high, the behavior is normal, and when the health index is low, the behavior is abnormal, right? And additionally, we noticed, now this is old hat right now, but at the time, we noticed that these different layers also captured these different patterns at different time scales without being given any prior information. So this time series, for example, is the power consumption time series. So there are five troughs, 5 peaks corresponding to the 5 weekdays, and then there's a trough corresponding to the weekend, right? And these LSTM models are very powerful. They manage to capture these trends and these patterns at the daily and the weekly level. Right? Additionally, what these models were able to do was to model correlations between sensors. So we have, for example, here we have a sensor which indicates the accelerator pedal position, and we can see that the APP and the CT sensor are actually very tightly correlated, right? And therefore, whenever this correlation is thrown off, these LSTM models are able to pick that up and flag an anomaly, right? And these are results from actual telematics data from engines. So, so this was quite kind of remarkable at the time. I know it all sounds very droll now, okay? And then you had these and then what we thought was, okay, so this technique of prediction can work when the time series is kind of quasi predictive, but what happens when the time series is not predictive at all, right? So in such a scenario, we decided, and it was just about the time when these encoder decoder models were starting to gain traction within the deep learning community. So we decided to try them out to see if we could use these models to reconstruct time series from normal behavior, and then use that reconstruction error at test time to determine whether or not anomalous behavior was occurring, right? And it turns out that this worked even better than LSTM-AD. This model is called LSTM-ED. and it's also been shown to work really well on non-predictive data, right? Okay, so these were the two kind of landmark kind of anomaly detection models, but this still left open the question of how do you actually diagnose what's going on when a fault is occurring? Which sensors out of the thousands of potential sensors are actually responsible for the fault? Where is the signal coming from? And in order to determine this, what we looked at was the distributions of these sensors under normal behavior and when the machine was healthy, and the distribution of these sensors when the machine was at fault, or the window in which the time window in which the machine was at fault. And using this, using the kind of discrepancy between the two distributions, you could get an assessment of which sensors have radically changed their distribution uh, in this current time window, and therefore might be largely responsible for this fault. And using that, you can actually get a ranking of the sensors responsible for a particular fault, as shown over here, and predict which, and then you would have to add domain knowledge on top of that to determine exactly what's going on, what fault has occurred within the system, right? And this was actually tried out in for health monitoring and prognostics of a gas turbine. And over here you can see, I mean, there are thousands of sensors, but we're just showing 6 in this particular figure. And this is like, on the left is normal behavior, and on the right are 2 sensors that are indicating kind of faulty behavior. And the kind of this method of distributional shift kind of picks that up, right? So another example is for this pulverizer mill. All right, and here the mill actually had to be shut down due to a catastrophic failure. So we got this data, and we showed that if you actually use these models in order to predict and diagnose what was happening, you could have detected the symptoms over 12 hours before the entire system was forced to kind of shut down. Right? And this can prevent catastrophic failure and thereby save a lot of money, right? But there's still additional problems to this, and the biggest of which was the fact that very often these systems have a shifting kind of shifting normal behavior. So, for example, in this figure over here, number 2, you can see that there's this kind of upward trend in this time series, and similarly, there might be sudden jumps in certain other time series where the mean shifts, right? And so, what you ideally want in a deep learning model is that it not only predicts an anomaly, but when there is a proper normal shift, or a concept drift, that the model just adapts automatically, right? And so we developed a model called online RNN-AD, where the key idea was that you continuously keep trying to predict what is going to happen in the future, and you get an anomaly score as before. But when the anomaly score is low, we do not update the model. But when the anomaly score is high, you use that anomaly score to actually update the weights of the model. And eventually, what will happen is that it will adapt to this new norm. If you don't do this, then what will happen is that, for instance, in this time series, you have this training set A, and then you try to use the model that is trained on A on this time series B. You won't get any anomalies because the behavior is fine. But as soon as you hit this time window C, things will start to. I mean, almost every other instance will be an anomaly because the model has never seen this kind of data before, right? But if you have this kind of online learning kind of paradigm where you allow the model to learn from the anomaly score, it will very quickly adapt to this new normal, right? And so yeah, so this is kind of another trick that we use for this online adoption is that we have to locally normalize the time series that is being fed into these models, because as you can see, the amplitude or the actual amplitude of the inputs keeps changing, and neural networks only kind of work well when they're given well-conditioned inputs within a certain small range. So you want to keep normalizing the data that's going into the network, and you do that by a kind of continuous normalization based on the last, let's say, n entries, last n time steps of the time series that you've seen. So anyway, so these are the steps. You do local normalization. You get a normalized input. You get a target sequence, and then you predict using your RNN. You get the prediction errors, and you get an anomaly score, and you update the RNN model based on the anomaly score. Right. So this simple idea works really well, and there was some independent validation of this recently by a paper. Freeman et al. At Flares 32 actually quoted that RNN-AD is the best performing algorithm for anomaly detection under concept drift. They evaluated RNN-AD against a whole bunch of other algorithms, state-of-the-art algorithms. All right. And yet another problem is dealing with very high dimensional time series, right? So, for instance, here you have, around 50 odd sensors, but you can see that there are tight clusters of sensors that are very highly correlated amongst themselves. And what you want to do is you want to have some kind of dimensionality reduction so that these sensors are kind of not, you're not overemphasizing these sensors, and you can kind of compress the space of the representation of these 50 odd sensors. And you can do that via kind of a sparsely connected dimensionality reduction layer, where you kind of have a lasso around the weights. You basically have a connected layer which kind of reduces dimensionality of the original sensors to a much lower dimensionality, and the weights of this layer are constrained by a kind of lasso constraint to ensure that very few of them are actually non-zero, and then using this kind of small, much lower dimensional embedding, can you reconstruct the original sequence that you saw here using an encoder decoder? And it turns out that if you do it this way, you get much better results when you're dealing with very high dimensional time series data. All right, so that was so anomaly detection was kind of problem number one. Problem number two was, now that you've detected an anomaly, can you determine how much further we have to go before the machine collapses? Right. This is called remaining useful life estimation. So this is typically how a system degrades, where initially the remaining useful life is very high, and over time, as the fraction of total life passes, the kind of reconstruction error blows up. And this is kind of how the remaining. So this is RUL, or remaining useful life, and this is how kind of when you're far away from failure, you have a lot of variance in your predictions about when the system is going to fail. It's very difficult to predict when a healthy system is going to fail. But once the system starts degrading, that is when you can actually say with more certainty and with more accuracy when a particular system is likely to fail. It's kind of common sense in a way. So we have a couple of models that we built. The first of which basically used the anomaly detection techniques that we have in order to get an estimation of the health index, right? And we did this for a NASA Turbofan data set, where we had several instances of failures of turbofans, right? Turbofan engines. And so we had these kind of degrading health index curves of turbofan engines. And what we did was we plotted all of these, and we got these health index curves based on our encoder decoder model, which was trained on normal behavior on the healthy part of the RUL life cycle. And so we got these curves for all the training samples which failed eventually. And at test time, though, we only got partial partial curve. So we only got the time series up to a particular point of degradation, And beyond that, we had to make an estimate of how long the system has before it actually degrades and fails catastrophically, right? And I mean, this is a slightly contrived data set, because in reality, failures are very rare, and the ability to train models with such small number of failures has to be developed. But in this particular data set, there were sufficient failure cases. But the way we did this was, we actually take this health index curve, which we only have till this point, and we try to match it with all the curves that we have from the training set, and we weigh the curves, and from that we can estimate that, look, this curve, this blue curve, is matching this green curve up to a particular point, and therefore the remaining useful life predicted as per this matching is, whatever this remainder of this green curve is, this r prime, right? Now we can do that for all the training set cases, and we can get good estimates uh, of remaining useful life. And this was the first algorithm, right? But the health index themselves, these curves themselves, are generated from the same encoder-decoder model that I just showed you for estimating kind of anomaly scores, right? Later on, we improved this, and we said that perhaps a better way to get get the health index curves is to actually look at the distance from the embedding space itself. So when you have a test instance, you look at the kind of embedding representation of that test instance, and you see how far that is from the embeddings of any of normal behavior. And the minimum distance is taken to be as the estimation of your health index, right? And it turns out much more robust to noise and handles missing values, etc., much better. And I'll just give you a kind of overview of how this is done. So this is your time series. You break it up into small windows. You pass each window through an RNN encoder from that same encoder decoder model, and you get embeddings, right, for each window. You then compare these embeddings to the embeddings of normal behavior, and you get a health index estimator. From this, you can then get a health index curve and how it's declining. And then you can use that to match against the set of curves that you have from the training set to get an estimate of your remaining useful life. The advantage here is that when we tried this on real data sets, right, you encounter a lot of problems such as missing values, right? So what we did to account for that was to allow a masking vector, which masks missing values with a 1, and a delta vector, which indicates when the last time a non-missing value occurred. And adding this information to the network, and telling it explicitly which values are missing in a time series and which values are not, makes life much easier for the network to learn. So these little tricks tend to help, and we got very good results for state-of-the-art results actually from these two methods for the Turbofan data set, and it was and these are all published, right? Okay. Um, but a difficulty that we found when we applied these techniques to real data is that in reality, as I mentioned, these systems don't fail very often. So you need techniques that will be able to adapt to situations where there is no failure data, right? So for instance, excuse me, there's some noise. So when there is failure data, and you can use these methods to do curve matching to find. Excuse me, there's some disturbance. Can you?
So whosoever is not using speaking, kindly mute all. So I'm not able to mute this person.
Okay. Okay, so it turns out that an even better technique to do this when you don't have access to failure data is and use the censored data that you have at your disposal. So, for instance, if you only have training data where you have time series up to this point, I'm sorry, it's getting very difficult to speak.
So actually, I'm not able to mute the speaker. I have muted many, but I'm not able to mute all. So let me see.
So, should I continue
Yeah,
or
now.
okay? Okay,
So this guy is not muting up actually. So there's someone in the system. So it's IT WebEx 4, and I'm not able to mute this guy.
okay. I mean, I can just continue then, I think. Okay. So the idea is that instead of actually trying to regress directly to a remaining useful life, what you can do is split the RUL into bins and try to use ordinal regression to predict the appropriate bin. And the advantage of that is that even if you have instances which have not completely failed, you can use the degradation that has happened so far and at least try to learn for the appropriate bins up to the degradation that has happened. So, for example, if you have a system that has degraded to, let's say, an RUL of 50%, you can predict the appropriate bins for 50% and mask out the remaining bins. And this is called using censored information, and this is very useful when you don't have access to a lot of failed instances. All right. All right, coming to the second kind of component of iSense is the automation of time series analysis using a model called TimeNet. Now, many of you might be familiar with this model called ImageNet, which is basically trained on lots and lots of images and is a generic feature extractor for vision. Right? So we did the same thing for time series, and we trained a model on lots and lots of time series, and we developed this model called TimeNet, which is an encoder-decoder model, which reconstructs lots of time series. And it turns out that now you can just use TimeNet as it is as a vanilla feature extractor for your time series classification tasks or other tasks that you might have. Right? So initial version of TimeNet was trained on 24 different data sets and generalized well to 30 different test sets that were not used in training. And you can see how cleanly it manages to kind of separate out the different types of data, right? And we actually wanted to see if TimeNet could be used out in a different domain. So we actually tried to use TimeNet as a feature extractor in the healthcare domain, where we tried to use it to extract features for a classifier to predict, physiological, using physiological parameters. Can you predict things like morbidity or phenotypes like sepsis? And it turns out that it got us state of the art results for those on the mimic data set. Just so this we found was quite amazing because we didn't have any domain knowledge about this field. We just used TimeNet on top of the physiological parameters of the patient, and using that we were able to get state of the art results. Right? So these are the kind of results that we got, right, for determining for patient phenotyping. Right? All right, and we actually combined TimeNet, and it turns out if you combine TimeNet with signal processing features from the domain, you can do even better. And we showed this on the PhysioNet challenge data set, and we have managed to kind of fuse features from TimeNet and signal processing. So domain knowledge still always helps, but TimeNet alone doesn't do too badly. So it's similar to kind of the vision story. Right, and so this was the result of kind of using both the TimeNet features and the signal processing features on a number of data sets and compared against the state-of-the-art techniques for time series classification. It turns out that just using TimeNet with signal processing features gives you, 22 out of 30 times you will win against all state-of-the-art techniques. Right? Okay, and then since then we've kind of evolved TimeNet a bit, and we've made it more current. We've built a convolutional version of TimeNet, which is based on multiple filters and kind of a ResNet sort of architecture for capturing different kind of different time scales. And the advantage of doing this is that things get much more interpretable because you can actually view the filters that get learned and determine what motifs are present in your time series, right? All right. And it turns out that this con TimeNet is kind of even better than the original TimeNet that we had, right? So I'm going to kind of move a little faster now. And then the next evolution in this is the fact that TimeNet now has to work in situations where you have very limited data. So the way we kind of handled this was using meta learning, right? In particular, gradient based meta learning. There's a technique called Reptile, which basically gives you, given a set of time series tasks, let's say T1 to TB, you want to estimate. You start with an initial set of parameters, and you tune these tasks to tune these parameters for these individual tasks, so as to optimize the performance across the test level performance across all these tasks, right? And then once you've done that, you end up with a kind of you end up with a set of parameters that you can start fine tuning with and do few shot learning, right? And this is what we did with meta TimeNet, and we managed to achieve state of the art results for few shot classification of time series using meta TimeNet, right? Okay. The next item was forecasting, right? In particular, the kind of forecasting that we are interested in today, although iSense is capable of many types of time series forecasting, but what we're really interested in today is process variable forecasting for kind of optimization problems. So the problem is as follows. So suppose you have a situation where you have a boiler or an industrial power plant, and you want to optimize the parameters or the control parameters of this power plant to maximize efficiency. Now you don't know what the optimal control parameters are, and every trial that you do costs a lot of money. So you have a budget of, let's say, T trials that you can use in order to estimate what the best parameters are. The parameters are these X's, and which yields the best response, which are these Y's. But the problem is you don't know the analytic form of this F, right? You don't know the mathematical form of F, and therefore you do not have access to its gradient. You can't do gradient descent, and therefore you need a technique for what we call black box optimization in order to estimate these parameters within a limited budget of T trials, right? And the interesting thing was that about the same time that we were looking at this problem, a paper emerged from Nando De Freitas's group called "Learning to Learn Without Gradient Descent by Gradient Descent," right? And it precisely dealt with this black box optimization problem. So f is the function you're trying to kind of optimize, and you don't know, you aren't aware of the functional form of f. And so what they did was they fed a recurrent neural network the historic kind of trial information over time. So let's say at time step 1, they tried a certain set of parameters and they got a certain set of responses. Then they feed that, and so xt minus 1 gives you yt minus 1, xt minus 2 gives you yt minus 1, which is then fed back into the RNN at the next time step. And this so at each time step, the RNN makes a prediction about what parameters to try, right? And this and you try to learn this RNN using an observed improvement loss, which is given over here. And and if you train it over many functions, they did it over functions that were sampled from Gaussian processes. If you train this over many functions, you actually and then you test it on unseen functions, it is able to optimize those unseen functions better than standard techniques like Bayesian optimization and other state-of-the-art techniques. So taking a cue from this, we decided to see what we could do for our industrial optimization problems. And so what we did was, we, instead of taking the observed improvement loss, which basically computed the difference between your current response and the best possible response you've got so far, we decided to use a regret-based loss and a discount factor to kind of give more importance to values that are kind of initially occurring in the sequence, right? Now, to deal with any range of values, we also use what we call incremental normalization, which is similar to the concept I described earlier, where you want to ensure that the values that are being produced and fed back into the RNN are within a certain range, right? So, and you do that using by continuously normalizing these values as they are produced by the recurrent model, right? And so it turns out that using this normalization function and using these techniques of incremental normalization, you can actually, and we trained these models on functions for which we actually had the optimal value. You basically using Gaussian mixture model, sampling from Gaussian mixture models of different dimensions. And therefore, since we had the analytic form, we could actually use the optimal value. Mind you, this was only used during training, so we could and then the advantage of using this was that we had these non-convex kind of functions, uh, non-convex sort of functions, which kind of approximate the variations that the model would see in real life, right? And the third modification we did was we incorporated domain constraints. So we don't want this model to start predicting pressure values of -200 or temperature values of 10,000 degrees Celsius. You want them to stay within range, and therefore you can impose domain constraints on this, and a penalty if those domain constraints are violated. And it turns out that if you do so, you can get much better results for actually optimizing these functions. Right, and it turns out that using these kind of techniques, these tricks, you can actually do better than what RNN-OI or the paper from Nando de Freitas's group did on optimization of spherical and from spherical functions and functions sampled from Gaussian mixture models. And it was better than standard techniques, heuristic based and numerical, evolutionary techniques as well, right? So, and using these domain constraint tricks, you can actually even apply it to industrial settings and ensure that your solutions are within range, right? All right, and the final piece of iSense, I have just enough time to cover this, is the notion of digital twins. In particular, what we wanted to do was incorporate domain knowledge about the structure of an IoT system into these deep models when they're making these predictions of remaining useful life, etc. So we thought, all right, what if we actually structure the network or create a network that would completely mimic the structure of the actual system? So, for example, here you have a turbofan, and here are the different components of a turbofan. So can you actually draw a neural network that mimics these different components, where each node has, you can model this as a graph where each node represents a subsystem within the larger system, and then connect those subsystems in the neural network depending on whether or not they're connected in the actual system, right? So we tried to see if this would lend any advantage in terms of predicting RUL, and it turns out that it does. And this is very exciting news, because now there are ways of actually incorporating kind of physical structure into these neural networks using GNNs, right? And so we use these GNN models to actually learn the structure. So if you model the graph based on the structure of the input, And so each node here represents the set of sensors that are present in that particular subsystem. And so S1, for example, represents the set of sensors going into subsystem D1. These are then converted into an embedding, and now each of these nodes is basically represented by an embedding vector, and then you can do a message passing like you do with GNNs to update these representations, and then finally use those representations with an attention over all the subsystems in order to predict remaining useful life. And it turns out that if you do that, you actually get much better results than you would if you did not incorporate these structural biases into your model. Right? And another application was in dealing with systems that have variable numbers of sensors, but where the underlying system is the same. So, for example, consider human activity recognition, where different people have different sets of sensors that are attached to them, or an industrial boiler, where it's the same underlying physical system, but the sensors vary from one customer or one company to another company. Right? And so the way we handle these situations is by modeling it as a graph again, where each node corresponds to, so let's say you have an input, you have a universal set of sensors for all possible systems, all possible boilers, or all possible activity recognition sensors, right? So this is your kind of universal time series. Now, for a particular instance, all you have to do is gray out the sensors that are not present, right? And feed them into what we call a core dynamics module, which is basically an RNN. And now you also try to get a conditioning vector which captures the structures of that particular instance. So, for example, the sensors that are actually available, they get connected to each other in the GNN, and then you use that the message passing system to come up with a kind of combination specific sensor embedding, or a sensor embedding that's specific to the set of sensors that are actually present in that particular instance. And doing that, you can actually get much better results for things like transfer learning across use cases. Because the question is, if your sensors keep changing, but your underlying system is the same, how do you transfer knowledge from your original system to your new system? Right? And how do you retain that knowledge and use it for things like zero-shot learning and fine-tuning and so on? And it turns out that using this kind of conditioning on the actual structure helps that zero-shot learning process. And this is being all right. So I think I have about 10 minutes. Um, so I'm going to just kind of cover what we've talked about. So basically, we talked about this iSense module, which is still kind of always evolving. And these are the four kind of big areas that we've kind of handled: health monitoring, pre-trained models, forecasting, and neural twins. Right? And these models or variants thereof have been used extensively and have been cited extensively. They're now being used for things like, NASA space shuttles, for detection in large hadron collider in Switzerland, and all sorts of applications have emerged from this work. These are a set of publications and kind of the applications that we have directly used these algorithms for. I think I'll now conclude here, and I'll open the floor for some questions.
So, Dr. Lovekesh, we thank you on behalf of the audience, IEEE SPS Delhi chapter and IIIT Delhi, for taking out your precious time for this webinar. It was really interesting. And now I request participants to may please put their questions in the chat window so that we can take them up.
we were able to practice. But the session was really interesting. And I have posted the relaxation and meditation technique on the day one, which on the presented, and the day after this meditation, which you
I'm sorry, is someone speaking? Because I hear somebody speaking, but I can't quite make out what you're saying.
So I'm hearing this from your mic, Dr. Lovekesh.
No, there's nobody here.
Can you just mute for a second? Because I
Sure.
am also able to hear someone speaking.
Dear participants, we completed a very meditation. We continue with our sessions on deep learning now. I request Shiva to open the session. Here. Thank you very much.
Surprise, so something is here. So, so I don't see messages in the chat window either. So,
Okay.
Dr. Lovekesh, would you like to speak a little bit about TCS and
Okay.
TCS, yeah,
I think
yeah,
a question has popped up, right?
yeah. Failure of a system is largely a OEM call. Predictive prevent is largely testing how fruitful can it be done using deep learning. Yeah. So there is a question for you.
So this all these systems are actually for OEMs. Uh, I mean, these systems have been deployed for OEMs. They're not. It's not something that TCS uses internally, although they have started using it for IT maintenance. But largely, large engineering manufacturing companies uh, that manufacture things like engines and trucks, they are the ones, or cars. They are the ones that are using these sorts of systems. Okay. So, I mean, so you want to know whether it can be used for a.
We request all the participants to use their minds. Thank you.
Yes, Sandeep, maybe you can unmute yourself and ask the question.
Change your role to like all of them figured out. So I'm just trying to
But I can't hear him. I can't hear you, Sandeep.
is there any other way which you can overcome the issue? No, Shaku. Like, once again, like, we need to be realistic. Yeah, then very fine. But you be not realistic to damage.
I'm sorry, I couldn't hear a word. I couldn't hear any of that. I'm sorry.
Am I audible?
Oh, yeah, now you are. Now you're
Yeah,
audible.
yeah, okay. So let's take a boiler plant example that you've taken. I mean, use case or something from user perspective, like a car. Let's take the car example, and we want to predict uh, uh, a a failure, detect an anomaly using these deep learning techniques, and we want to predict a failure of a particular component. Now, what I meant by a OEM's call is I am the user of certain components or a set of components integrated as a system. I have been given certain leaflets. I'm the maintenance guy, for example, and the user is somebody else. He comes down to me for checking purposes, and I run some tests, right? So whenever I run the test, I know what are the which my test result should fall. I mean, if there is a pot meter reading from a particular sensor, I should get it between 0 and 5, let's say. So in that sense, every every system, every component has been categorized by the OEM for the maintainability. So when we say that it's an OEM call, what I mean is OEM has run certain amount of tests on each and every components and has decided a limit which may be 80% of its actual limit. Let's say if a car tire can run for 200 kilometers without a change, the OEM will say run it for 160 kilometers. So what I intend to ask is how well these parameters can be actually used for anomaly detection and preventive maintenance in a predictive manner if it has already been taken care of by from the OEM or from the perspective of manufacturing itself. I'm done. Thanks a
Right.
lot.
So OEMs will give you an initial how that product is going to degrade when you use it is not something the OEM will necessarily have control over, and you will not necessarily be visiting the OEM manufacturer every day to get your car serviced or whatever, right? The idea is to move away from time-based maintenance completely and only visit the OEM when and move towards condition-based maintenance, where you only visit the OEM when your sensors are actually telling you that something is going wrong. Right. So the idea is not to so real time feedback from these sensors is something that we're looking at. Not, I mean, we're not trying to say that the OEM doesn't have a role. The OEM has a role, but the OEM can't sit with you every minute and keep testing your car every day, right? That's what sensors are for. I mean, let me put it this way. I'm sorry. Is there a question?
No, Dr. Lovekesh, there seems to be, I don't know what is the problem, but there seems to be some noise from somewhere background. We don't see anyone speaking.
Okay.
Yeah, please go on.
Yeah, no. So what I was saying was, right now you probably go to your let's say garage.
People who are graduate, under post graduation or
Looks like some parallel meeting is going on. Either we have mixed up or something has happened.
we having very
Okay, so maybe Dr. Lovekesh, maybe you can take the questions offline. Maybe by people can read your papers. So, uh,
Yes, please.
is it okay if we just wind up the session?
Right, that's fine. That's
Yeah,
fine.
so thank you so much for taking out time and joining here. So we once again thank you for this wonderful session. And we have recorded the session, so if anyone wants, we'll also share the recording. Thank you all. Thank you. Have a
Thank
good
you.
day. Bye-bye.